Have you ever felt that swirl of information overload? You're trying to figure out what really separates a good Python coder from a truly great one.
Yeah, or maybe you're just really curious about what strong proficiency in Python actually means, beyond just knowing the basics.
Exactly. Well, you're in the right place. Today, we're doing a deep dive into exactly that. We're going way beyond just, like, knowing the syntax.
We want to explore the whole picture, a holistic competency. We're drawing insights from the Proficient Python Developer's Handbook and also the Python Proficiency Playbook.
Right. And our mission for you today is basically to pull out the most important nuggets of knowledge from these sources.
Yeah, give you a shortcut, sort of, to understanding that architectural thinking and the rigorous engineering discipline that really defines a proficient Python developer.
We'll try to uncover some surprising bits and connect the dots so you can see the bigger picture. Building robust, scalable, maintainable software systems, the kind that solve real-world problems. Okay, so let's start by really unpacking this idea of strong proficiency. We all write code that works, eventually.
Yeah.
But what's that next level? How do you get beyond just functional?
It's a great question. It's fascinating because it signifies the ability to not just, write code that runs, but to actually architect systems, to build and deploy them so they're robust, scalable, maintainable.
So it's bigger than just a script file.
Much bigger. The real question becomes, how does your code fit into this larger ecosystem? The tools, the practices, the principles that ensure quality and reliability. Your code doesn't exist in a vacuum, right?
Right. And when we talk about proficiency, that often leads to talking about the Pythonic way. I hear that term a lot. It sounds almost like a philosophy. What does it actually mean in practice?
You've hit on a key point there. It really means writing code that's expressive, efficient, and idiomatic. It adheres to Python's core design philosophy. You often see it inspired by the Zen of Python. And this approach is crucial because it leads to code that's easier to read, easier to maintain, and often actually performs better. It's like the fundamental distinction between someone who just knows the syntax and someone who understands the language.
And a classic example of that Pythonic spirit must be list comprehensions, right? And dictionary comprehensions, too. They really change how you handle data.
Oh, absolutely. List comprehensions are like this super compact way to build lists. You describe what you want in each item instead of writing out all the steps of a for loop.
Like making a list of squares.
Exactly. I for in range for boom, done, one line. And what's surprising maybe is that it's not just about being short and sweet.
Ah, right, the performance aspect.
Yeah, they can often be faster than the equivalent for loop. It's because a lot of that work is pushed down to the C level in Python's implementation. So you get the C-level optimization almost for free. Same idea applies to dictionary comprehensions, like I for I in range 2, it will use 0 for even squares.
And building on that efficiency idea, what about generator expressions? They look similar, but they're different in a key way.
They are. Very important difference. While list comprehensions build the whole list in memory right away.
Which can be a problem for huge lists.
Exactly. Generator expressions give you incredible memory efficiency for large data sets because they yield items one at a time only when you ask for them. You use parentheses instead of square brackets.
So I for I in range 100,000 versus I for I in range 100,000.
Precisely. For really massive data sets, generating items as needed is crucial for scalability. Stops you from blowing up your memory usage.
Okay, makes sense. Then there's the with statement we see with open all the time, and it just, magically closes the file. What's the deeper magic there?
Well, it's cleaner than writing try.finally blocks, that's for sure. But the real insight is how with provides robust automatic resource management. It guarantees that resources, files, network connections, locks, whatever, are properly set up and crucially torn down, even if errors happen inside the block.
And it works with more than just files.
Oh, yeah. Anything that implements the context manager protocol, basically. Objects with special enter and exit methods can be used with. It abstracts away that setup and cleanup logic.
So it's about safety and clarity.
Exactly. A proficient developer understands that using with signals a deeper concern for both resource safety and keeping the main logic clean. You can even write your own custom context managers, maybe one that times how long a block of code takes, for instance.
Okay, that's a solid Pythonic foundation. Now let's move up a bit into some more advanced concepts. Decorators. Those little @ symbols you see sprinkled above function definitions. What's the deal with them?
Decorators. They're higher order functions. Essentially, they wrap other functions, letting you extend or modify their behavior without messing with the original function's code directly.
So you can add things like logging or checking permissions.
Precisely. They're invaluable for separating what we call cross-cutting concerns. Things like logging, timing, authentication, caching, stuff that applies to many functions but isn't part of their core job.
And the surprising thing is how cleanly they do it.
Yeah, I think so. They let you separate what a function does from how its behavior might be enhanced or monitored. It helps avoid that spaghetti code, where core logic gets tangled up with secondary tasks. Applying a timer decorator, for example, measures execution time without you ever adding timing code inside the function itself. And using functools.wraps is a best practice to preserve the original function's metadata.
Got it. Now, for something that often feels a bit mystical, metaclasses, they get described as the class of a class. What's their actual purpose? And honestly, how often do you really need them?
Metaclasses, right? They define how a class itself is created. Think of type as the default metaclass. By defining your own metaclass, you can intercept class creation and modify it.
So you could enforce certain rules on classes.
Yes, or dynamically generate parts of a class, or enforce patterns like the singleton pattern across multiple classes. They are incredibly powerful. You see them used under the hood in big frameworks like Django's ORM or Scholalchemy to do some complex magic.
But for everyday coding.
That's the key point. While they're powerful, they are highly advanced. For most application-level development, using metaclasses can make your code significantly more complex, much harder to understand and maintain.
So understand them, but maybe don't rush to use them.
Exactly. A proficient developer knows how they work, but more importantly, knows when their use might actually be justified. And honestly, for the vast majority of projects, that's rarely. It's a very specialized tool for very specialized problems. Don't reach for it unless you have a really, really good reason.
Okay, that's clear. So from those advanced language features, let's pivot to something crucial for performance and scale. Concurrency. And we have to talk about the GIL, the global interpreter lock. It gets a lot of blame. What is it really, and how does it shape Python concurrency?
The GIL, yes. In CPython, the most common Python implementation, the GIL, is a mutex, a lock, that protects access to Python objects, preventing multiple native threads from executing Python bytecode at the exact same time within a single process.
So multiple threads can't run Python code truly in parallel on multiple CPU cores.
Within one process for CPU-bound work, that's generally true. The surprising thing isn't just its existence, but how often performance issues get blamed on the GIL when the real bottleneck might be something else entirely, like I/O.
Okay, so it impacts CPU-bound tasks differently than I/O-bound tasks.
Critically different. For CPU-bound tasks, heavy calculations, image processing, that sort of thing, multiple threads won't give you true parallelism because only one thread can hold the GIL and execute bytecode at a time. In fact, the overhead of threads switching might even slow things down slightly.
But for tasks waiting on things, like network requests.
Exactly. For I/O-bound tasks waiting for network responses, reading writing files, database queries, Python threads are smart enough to release the GIL while they wait. So while one thread is blocked waiting for data, another thread can grab the GIL and run. This allows for concurrency, even if not true parallelism. Understanding this distinction is absolutely paramount for picking the right concurrency model for your specific problem.
Okay, so given that GIL behavior, what are the main tools Python gives us to handle concurrency effectively?
Well, the first one is threading, using the built-in threading module, often via the higher-level concurrent.futures thread pool executor. As we just discussed, this is really ideal for I/O-bound tasks.
Like downloading multiple web pages at once.
Perfect example. While one thread is waiting for a server response, another can be starting a new download request. Get overlap, making things faster.
Right. But if my task is chewing up CPU cycles,
then threading isn't your friend because of the GIL. That's where multiprocessing comes in, using the multiprocessing module, again, often via concurrent.futures process pool executor.
And this gets around the GIL.
It does, because it creates separate processes, each with its own Python interpreter and its own memory space. Since they are separate processes, the GIL in one doesn't affect the others. This gives you true parallelism for CPU-bound tasks, letting you use all your CPU cores.
Like doing complex math calculations in parallel.
Exactly.
Yeah.
Calculating Fibonacci numbers, crunching large data sets, things like that.
Okay, and then there's the third major approach, which feels more modern. Asynchronous programming with Asyncio.
Right. Asynchronous programming using Asyncio, this is a different model altogether. It typically uses a single thread and an event loop for cooperative multitasking. It's fantastic for high-throughput I/O-bound tasks.
Like web servers handling thousands of connections.
Precisely. Because tasks explicitly await when they're doing I/O, they yield control back to the event loop, which can then run another ready task. It's very lightweight compared to threads, making it super scalable for managing tons and tons of concurrent I/O operations, like in a busy web server or a network client talking to many peers.
So the choice really depends on the bottleneck.
Absolutely. Connecting this to the bigger picture, knowing when to use each is critical. A proficient developer analyzes the problem. Is my program spending most of its time waiting, I/O bound, or is it crunching numbers, CPU bound? Then they select the right tool. Threading for I/O, multiprocessing for CPU, Asyncio for high-volume I/O. The concurrency decision matrix in the sources lays this out really well.
Makes sense. Now let's talk about something often dreaded, especially around interviews. Data structures and algorithms, DSA. Are they really just for interviews, or do they have practical importance for a proficient Python engineer?
Oh, they're far more than just interview fodder. For a proficient engineer, DSA are fundamental building blocks for designing efficient, scalable systems. It's absolutely practical.
How so? I mean, Python has built-in lists and dictionaries, right?
It does, and they're great. But knowing how they work internally and when to choose one over the other or when you might need something different is crucial. What's fascinating is how the choice of data structure directly impacts performance, memory usage, scalability.
Can you give an example?
Sure. Think about Python's dictionary, which is basically a hash table. Why do we use it so often? Because it gives us average, O1, constant time, lookups, insertions, deletions, fantastic for caches, or just quickly accessing data by key.
Okay, fast look.
But what if you need your data to be ordered? Or you need to efficiently find all items within a certain range. A dictionary isn't great for that. That's where something like a balanced binary search tree might come in, even though its lookups are O log n, which is slightly slower than O1. Databases often use tree-like structures internally for exactly these reasons, ordered data and efficient range queries. So the choice depends entirely on the access patterns you need.
I see. And it's not just the structures, but the algorithms, the approaches to solving problems.
Absolutely. Take the greedy approach. It's often simple and fast. You make the choice that looks best at the current moment. It works perfectly for some problems, like the fractional knapsack problem, where you can take parts of items. Easy, fast, optimal.
But it doesn't always work.
Right. It only works if the problem has this special greedy choice property. Contrast that with dynamic programming, DP. DP is usually more complex to think about initially, but it's more powerful for certain problems. It breaks the problem down into overlapping subproblems, solves each subproblem only once using memorization or tabulation, and combines the results to guarantee a globally optimal solution.
Like the 0-1 knapsack problem.
Exactly, where you can't take fractions of items. A simple greedy approach fails there, but DP finds the best combination. Understanding these different paradigms lets you pick the right strategy for the job.
And underlying all this performance discussion is big O notation, still essential.
Non-negotiable. Absolutely essential for predicting how your system will scale. An algorithm that's ON squared might seem fine when you test it with 10 items.
But explodes with a million items.
Precisely. It quickly becomes a crippling bottleneck as your input size grows. A proficient developer doesn't just write code that works now. They have an intuitive grasp of its performance characteristics and how it will behave under real-world load. They think about scalability from the start.
Okay, so we've talked code style, advanced features, concurrency, DSA. What about putting it all together in a professional context? How do you structure projects and ensure they're production ready? This is about the professional toolkit, right?
Exactly. It starts with a clean, modern project structure. A really common and recommended best practice is the SRC layout.
Why the SRC folder?
It clearly separates your actual package source code from everything else, tests, documentation, configuration files. It makes the project cleaner, easier to navigate, and avoids some common pitfalls when packaging and installing.
And for managing all the project settings and dependencies, things used to be scattered across setup.py, requirements.txt.
Yeah, it could be messy. No, the strong trend, and a very good one, is using pyproject.toml. It's becoming the single, standardized, declarative file for almost everything. Project metadata, build system requirements, dependencies, and configurations for tools like linters and formatters.
So one file to rule them all.
Pretty much. It centralizes everything, making project setup much more consistent and reliable. It's a big step forward.
And alongside that, we absolutely need virtual environments, right?
Oh, indispensable. Using Ven and pip creates isolated environments for each project. This prevents dependency conflicts, Project A needing version 1 of a library, while Project B needs version 2. It ensures reproducibility. Pip install.je.dev within an active ven is like standard practice for setting up a development environment. Absolutely crucial.
Okay, structure and dependencies sorted.
Yeah.
Now the absolute non-negotiables. Version control, code quality, testing, pillars of professional work.
Couldn't agree more. For version control, Git is standard, obviously, but it's about using it effectively. Workflows like feature branching are key for collaboration. You work on new features or fixes in separate branches, get them reviewed via pull requests, and only merge stable code back into your main branch. Keeps things organized and traceable.
And ensures the main branch is always potentially deployable.
Exactly. Then, automated code quality. Tools like Black are fantastic. It's an uncompromising code formatter, just run it, and your code style becomes consistent. No more arguments about spacing or line breaks.
Takes the whole style debate off the table.
It does. And then there's Rough. It's incredibly fast and combines the power of many older tools, linters like Flake8, import sorters like isort, even tools that help upgrade syntax like PyUpgrade. It catches potential errors and style issues super early in the process. Integrating these into your workflow, maybe with pre-commit hooks, is a huge win.
And testing. PyTest seems to be the crowd favorite now.
It really is, and for good reason. PyTest makes writing tests simpler and more powerful. Its assert introspection is amazing. When an assertion fails, it tells you exactly what the values were, making debugging much easier.
Compared to just assertion error.
Right. And its fixture system is brilliant for setting up test preconditions, like database connections or test data, and tearing them down cleanly. It makes tests reusable and less repetitive. Plus, parameterization lets you run the same test logic with many different inputs easily. A solid test suite using PyTest gives you confidence to refactor and add features without breaking things.
Okay, tests pass, code looks good. Now we need to get it running somewhere other than our own machine. Deployment pipeline time.
Right. And the first big piece here is often Docker. Containerization with Docker solves that classic, well, it works on my machine problem. You define your application's environment in a Docker file, maybe orchestrate multiple containers with docker-compose.yaml.
So you package the app and all its dependencies together.
Exactly. It ensures your application runs in the exact same consistent environment everywhere: development, testing, staging, production. Huge for reliability.
And then automating the build, test, deploy process.
That's CI/CD. Continuous integration, CI, means automatically building and testing your code every time you push changes, catching issues early. Continuous delivery or deployment, CD takes it further, automatically deploying your tested code to staging or even production. It speeds up releases and reduces manual errors. Tools like GitHub Actions, GitLab CI, Jenkins are common here.
And managing the servers and databases themselves.
That leads to infrastructure as code, IAC. Instead of manually clicking around in a cloud console, you define your infrastructure servers, databases, networks, and configuration files using tools like Terraform or AWS CloudFormation.
Creating infrastructure like software.
Precisely. You get version control, repeatability, automation, all the benefits of software development applied to managing your infrastructure. Makes things much more robust and scalable.
Okay, wow. That's a lot of pieces. Let's try to bring it all together. How about a real-world example? Maybe building, say, a production-grade web scraping API. That seems like it would touch on many of these concepts.
That's a perfect example. You can really see how Asyncio, maybe a web framework like FastAPI and Docker, integrate to build something efficient, scalable, and deployable.
So what would the goal be? Scrape some data and serve it up?
Yeah, let's say the functional requirements are scrape quotes from a website, maybe authors too, and expose this data via a REST API. But then you have the non-functional requirements, which are just as important for production grade. Things like high throughput, handling many requests, low latency, responding quickly, scalability, handling more load later, and maintainability, easy to update.
Okay, so how would we leverage the things we've discussed? Where does Asyncio fit in?
Well, web scraping is heavily IO-bound, right? You're waiting for websites to respond. So asynchronous scraping is a natural fit. We'd use Asyncio along with an async HTTP client like HTTPX. We could have a function, maybe scrape quotes, that concurrently fetches multiple pages. This dramatically speeds up the scraping compared to doing it sequentially. Then maybe use Beautiful Soup or a similar library for parsing the HTML once we get it.
Got it. Faster scraping. And for the API part, serving the scraped data.
A modern async framework like FastAPI would be ideal here. It's built on Asyncio, so it integrates perfectly with our async scraper. Plus, FastAPI leverages Pydantic models for automatic request and response validation. You define a, quote, model, say, and FastAPI handles validating incoming data and serializing outgoing data based on that model.
And gives you that nice interactive documentation automatically.
Yep, the Swagger UI OpenAPI docs are built in, huge productivity booster, so you get a high-performance, validated API with minimal boilerplate.
Okay, async scraping feeding into an async API. How do we package and deploy this reliably?
Back to containerization. We'd write a Docker file to package the Python environment, our scraper code, the FastAPI application, everything needed to run it. This container ensures it runs the same way anywhere. We could use Docker Compose if we needed other services, like maybe a database eventually.
In testing this whole thing.
Absolutely crucial. Robust testing in CI. We'd use PyTest. We'd write unit tests for the core scraping logic, making sure it parses HTML correctly. And we'd write integration tests